For, well, centuries, humanity has looked up at the night sky, asking some really deep questions. How did it all begin? What's it made of? Where do we fit
The
in?
big ones, yeah.
The amazing thing about the 20th century, though, was how these ancient sort of philosophical questions started turning into problems physics could actually, well, get its teeth into.
Right. Things became testable.
Discoveries like finding out there were other galaxies, whole other island universes out there.
And developing general relativity to describe gravity, that was huge.
Absolutely key. It shifted everything.
It moved from pure speculation
Mhm.
to, models we could write down mathematically and observations we could actually go out and make.
And that transformation is exactly what we're diving into today. We've got a stack of source material here, excerpts from a book on modern cosmology. It pulls together reports from a doctoral school on relativistic cosmology held over in Italy. So basically, we're getting insights straight from the experts who are really wrestling with these big cosmic questions.
Yeah, think of them as snapshots from the research front lines. They highlight the key evidence, the theories people were using, and importantly, the puzzles that were driving the field. Some still are, actually.
So our mission for this deep dive is simple. Take these sources, dig in, and pull out the most important nuggets of knowledge and insight for you.
Help cut through the jargon a bit.
Exactly. Help you understand what these experts thought was really significant about our universe, its origins, how it works. It's kind of a shortcut to getting genuinely well-informed on some, let's face it, pretty mind-bending topics.
We'll look at the evidence, the models, and yeah, some of those big unanswered questions that still linger.
Okay, let's get started. When we talk about the early universe, the picture that really emerges from these sources is grounded in the hot Big Bang model. And maybe the most compelling piece of evidence they discuss is the cosmic microwave background, the CMB.
Ah, the CMB. The afterglow of the Big Bang, right?
That's the one.
Our sources tell that great story, its accidental discovery back in '65. Penzias and Wilson at Bell Labs.
Right, with the bighorn antenna.
Yeah, they were doing satellite communication work.
Yeah.
They kept picking up this persistent static, this noise they just couldn't explain, couldn't get rid of.
No matter where they pointed the antenna.
Exactly.
Yeah.
And they famously even cleaned out pigeon droppings from inside the horn, thinking maybe that was it.
I love that detail. Pigeons holding up cosmology. So how did they figure out it wasn't just noise? Or birds?
Well, eventually they got wind of a group in Princeton, people like Peebles and Dick, and they had actually predicted, theoretically, that if the universe started hot and dense, there should be this faint radiation left over, an afterglow.
They predicted a temperature too, didn't they?
They did, yeah. They estimated something like 10 Kelvin. So when Penzias and Wilson described their persistent, unexplained 3 Kelvin signal, the Princeton group immediately knew. That was it. That was the relic radiation they were looking for.
Incredible.
Yeah.
So for us today, what is the CMB conceptually? What are we actually looking at?
It's like looking at a baby picture of the universe, taken when it was only about 380,000 years old.
Tiny.
Yeah, cosmically speaking. Before that time, the universe was this incredibly hot, dense soup of plasma. Light particles, photons, were just constantly scattering off free electrons and protons. Couldn't travel far.
Like being inside a dense fog?
Exactly. But as the universe expanded, it cooled down. Eventually it got cool enough for electrons and protons to combine and form neutral hydrogen atoms. That's called recombination.
And suddenly the fog lifted.
Pretty much. The photons were suddenly free. They could travel across the universe without constantly bumping into charged particles. The CMB is that light released at that moment that's been traveling towards us ever since. It comes from what we call the surface of last scattering. A snapshot of the universe then.
And this snapshot, this picture, it isn't perfectly uniform, is it? There are tiny temperature differences.
And that is where the real gold is. Those tiny fluctuations, maybe 1 part in 100,000, they aren't just random noise. They are incredibly important. They're the fingerprints of the very early universe.
What do they represent?
They show us tiny variations in density and temperature in that primordial plasma right before the photons were set free. We analyze these variations using statistics, specifically something called the power spectrum.
Okay.
The power spectrum basically tells us how strong the temperature fluctuations are on different angular scales across the sky. Are the hot and cold spots typically big, small, or some mix?
I think I've heard about the Doppler peak in that spectrum.
Yes, although the sources we looked at actually prefer the term acoustic peak, and it's a better description, really.
Why acoustic?
Because before recombination, that plasma of matter and radiation wasn't static. It was oscillating, sloshing back and forth under gravity and pressure, literally like sound waves propagating through a fluid.
Wow, sound waves in the early universe.
Yeah, cosmic sound waves. These oscillations imprinted characteristic patterns, specific scales, onto the temperature map we see in the CMB. Those patterns show up as peaks in the power spectrum.
And these acoustic peaks, they tell us fundamental things about the universe.
Oh, absolutely. Huge things. For instance, the location, the angular scale of the very first, the biggest acoustic peak is incredibly sensitive to the overall geometry of the universe.
Oh, so.
Measuring where that first peak falls provides really strong evidence that the universe is spatially flat.
Flat like a sheet of paper, not curved like a ball.
Exactly. On the largest scales, the geometry is Euclidean. In cosmological terms, it means the total density parameter omega tot, the ratio of the actual density to the critical density needed for flatness, is extremely close to 1.
That's amazing, just from measuring the size of the biggest temperature blobs on the CMB map.
Pretty much. It's one of the cornerstones of modern cosmology.
What about the other peaks? The smaller ones?
Measuring those higher peaks accurately gives us even more information. The pattern, the relative heights and positions of the peaks, is sensitive to other key ingredients, like the sound speed in that early plasma. And it gives us one of the most precise ways to measure the amount of ordinary matter, or baryonic matter, the stuff we're made of in the universe, the baryon density, omega.
The sources also mention CMB polarization. What does that add? Is it like polarized sunglasses?
Kind of, yeah. Polarization is about the orientation of light waves. The physics of scattering predicts that the light from the last scattering surface shouldn't just have temperature fluctuations, but also a specific pattern of polarization.
And why is that useful?
Well, the theory of these acoustic oscillations predicts a very specific relationship between the temperature peaks and the polarization peaks that should be sort of interleaved or out of phase.
Out of phase.
Because the temperature fluctuations are mainly driven by density variations, while the polarization is more sensitive to the velocity of the plasma flowing into or out of those density clumps. In a sound wave, density and velocity are naturally out of phase. Detecting that specific interleaved pattern in polarization gives us huge confidence that we really are seeing the effects of coherent acoustic oscillations. It confirms the whole picture.
Got it. And the fact that these fluctuations were detected at roughly the expected level, that tiny 1 part in 100,000.
That was a massive boost for the whole idea of structure formation through gravity. It showed that the seeds needed to grow today's galaxies and clusters really were there in the early universe.
Tiny seeds for giant structures.
Exactly. Our sources also point out that theories like cosmic inflation provide a natural mechanism for generating these initial fluctuations, especially the ones on the very largest scales, scales that were actually bigger than the observable horizon at that time.
Super horizon modes.
Right? Inflation can stretch tiny quantum fluctuations to those enormous sizes. Now, finding these modes is consistent with inflation, but the sources caution it's not necessarily definitive proof of inflation itself. Other mechanisms might exist.
Okay, so the CMB gives us this amazing snapshot and the seeds. How do we build the models to describe how the universe evolves after that, the expansion and all that?
That's where cosmological models come in. The simplest ones, and the foundation really, are the homogeneous and isotropic models. These are based on the Friedman-Robertson-Walker metric, the FRW metric.
Homogeneous and isotropic meaning the same everywhere and in every direction.
On large enough scales, yes. That's the simplifying assumption.
But hang on, the universe isn't perfectly smooth. We have galaxies, clusters, voids. It looks pretty clumpy.
That's a really important point, and the sources are clear on this. The FRW model is an approximation, a description of the average behavior. They do mention more complicated exact solutions to Einstein's equations that don't have that perfect symmetry. Things like LTB models, Sicker's models, even Swiss cheese models where you embed lumps in a smooth background.
So the real universe is messy.
The real universe definitely belongs to that messier class of solutions without perfect symmetries. But remarkably, the simple FRW model works incredibly well for describing the overall expansion and evolution on the largest scales.
And how does that model describe the expansion itself?
It's governed by Friedman's equation. You can actually get a feel for it using Newtonian gravity, just thinking about energy conservation for an expanding sphere of matter. General relativity gives you the precise form.
Okay.
This equation tells us how the scale factor evolves over time. The scale factor, usually called RT or AT, is like a cosmic measuring stick. It tells you how distances between distant objects, ones not bound together by local gravity, stretch as the universe expands.
So as a T gets bigger, the universe gets bigger.
Right. And this stretching affects light too. The wavelength of light traveling from distant galaxies gets stretched along with space. That's redshift. The light becomes redder, longer wavelength. The further away the galaxy, the more the universe is expanded while the light traveled, the greater the redshift.
What about things moving within the overall expansion, like galaxies whizzing around inside a cluster? Those are peculiar velocities.
Exactly. Motions relative to the smooth Hubble flow. And the sources highlight something interesting here. These peculiar velocities tend to decay away as the universe expands, proportional to 1a.
So the expansion kind of smooths out random motions?
In a sense, yes. The stretching of space dominates over time. Particles tend to get carried along with the Hubble flow eventually, regardless of their initial peculiar velocity.
Now, the sources bring up something called the flatness problem. What's that about? Sound like it relates to the CMB finding.
It does, and it's a major puzzle for the standard Big Bang model without something like inflation. Remember how the CMB tells us the universe is very close to flat today, omega tot 1?
Yeah.
Well, according to Friedman's equation, if the universe isn't perfectly flat, any initial curvature gets amplified as the universe expands in the standard model. For omega tot to be so close to 1 today, it must have been unbelievably, absurdly close to 1 in the very early universe.
Wait, how close?
The density term would have had to be tuned to match the curvature term to something like 1 part in 10 to the 60th power near the Planck time. It looks like incredible unnatural fine-tuning. Why would it start out so perfectly balanced?
Seems unlikely to happen by chance.
Exactly. It feels like a massive coincidence.
And inflation is the proposed fix for this.
It's the leading proposed solution, yes. Inflation is this idea of a very, very brief period of incredibly rapid exponential expansion right at the beginning.
Faster than normal expansion.
Much faster. During inflation, the universe is thought to be dominated by a type of energy density with negative pressure, maybe related to vacuum energy or a hypothetical scalar field.
Negative pressure, like anti-gravity.
Sort of, yeah.
Oh,
It
yeah.
drives this runaway expansion. And crucially, in Friedman's equation, during this exponential expansion, the curvature term shrinks relative to the density term extremely rapidly. Inflation effectively stretches any initial curvature completely flat.
So it doesn't matter what the initial curvature was.
Pretty much. If inflation lasts long enough, it drives omega tot so close to 1 that it's essentially indistinguishable from flat today. It solves the fine-tuning problem automatically.
Okay, that makes sense. Now, you mentioned vacuum energy and negative pressure. That sounds a bit like what we think is happening today with the accelerating universe.
It does, doesn't it? And yes, this is another huge discovery highlighted in the sources, the evidence that the universe's expansion isn't slowing down due to gravity, but actually speeding up.
And that came from supernovae.
Primarily, yes. Specifically, type Ia supernovae. These are explosions of white dwarf stars that reach a certain mass limit, and they are incredibly useful because they act as standard candles.
Meaning they all have roughly the same true brightness.
Exactly. Their peak intrinsic luminosity is remarkably consistent. So by measuring how bright they appear to us, we can figure out how far away they are.
And what did looking at very distant type Ia supernovae show?
They show that the really distant ones, the ones that exploded billions of years ago when the universe was younger, looked fainter than expected.
Fainter means further away.
Further away than they would be if the universe had been expanding at a constant rate or slowing down. The only way they could be that far away is if the expansion of the universe has actually accelerated at some point between then and now, pushing them further out.
That acceleration needs
Something with negative pressure dominating the universe's energy budget today. Something acting like a cosmological constant, lambda, or maybe a more dynamic field, often called dark energy or quintessence.
So putting it all together, CMB, supernovae, other observations, what's the standard picture, the cosmic recipe that the sources describe?
The consensus picture, strongly supported by all this data, is a universe that is spatially flat, omega tot equals 1, just as inflation predicts and the CMB confirms. And its energy budget today is dominated by this mysterious dark energy component.
How much dark energy versus matter?
The typical numbers cited are around 70% dark energy, omega lambda 0.7, and about 30% total matter, omega 1.3. And remember, most of that matter isn't even the ordinary baryonic matter we know.
Right, we'll get to dark matter. But first, the sources also mention causal and visual horizons. Why are those concepts important here?
They're fundamental for understanding connectivity in the universe. A causal horizon marks the boundary of the region that could have possibly influenced us, or that we could influence. The visual horizon, or particle horizon, marks the boundary of the region. We can actually see the furthest distance from which light has had time to reach us since the Big Bang. The key point the sources stress is that in an expanding universe governed by general relativity, these horizon scales always grow. Distances between objects increase, yes, but the actual physical size of the region we're connected to or can see doesn't shrink. Once 2 points are in causal contact, they stay in contact, even as they move further apart due to expansion.
Got it. Okay, so we have the Big Bang, the CMB seeds, a model for expansion driven partly by dark energy. But how do we get from those tiny CMB ripples to the huge structures like galaxies and clusters we see today, the lumpy universe?
That's the story of structure formation, and the main driver is good old gravity. Gravitational instability.
Meaning?
The basic idea is simple. Regions that started out slightly denser than average in the early universe, thanks to those CMB fluctuations, had slightly stronger gravity. They pulled in more matter from their surroundings.
Rich get richer.
Exactly. Over billions of years, gravity amplifies these initial tiny density differences. Denser regions grow denser, less dense regions become emptier voids, and eventually the densest regions collapse under their own gravity to form the things we see: galaxies, groups, and massive clusters of galaxies.
And where did those initial seeds, those density fluctuations, actually come from in the first place?
Well, as we touched on, inflation theory offers a very compelling explanation, one the sources definitely highlight.
The stretching of quantum fluctuations.
Precisely. Quantum mechanics tells us that even seemingly empty space is fizzing with tiny temporary fluctuations in energy and fields, microscopic quantum jitters. During inflation's super rapid expansion, these microscopic quantum fluctuations in the field driving inflation get stretched to enormous astrophysical scales.
So quantum fuzziness becomes cosmic structure?
That's the idea. Inflation takes quantum uncertainty and blows it up to become the seeds for all the galaxies and clusters. The amplitude of these seed fluctuations is naturally related to the energy scale of inflation itself.
Okay, so inflation might lay down the pattern.
That's the leading theory. And these patterns are mostly density perturbations, places slightly denser or less dense than average. The sources discuss how these evolved gravity makes the density perturbations grow over time, growing modes, though there are also decaying modes. They also mention something called vorticity modes.
Vorticity, like swirling.
Yeah, like eddies or swirls in the cosmic fluid that don't necessarily involve density changes. But gravitational instability theory predicts that these vorticity modes should decay away as the universe expands. So the large-scale velocity field-driving structure formation should be essentially curl-free, flowing into dense regions, not swirling around.
All right, so gravity grows structure from the seeds. But when we look at how things move, stars and galaxies, galaxies and clusters, there seems to be way more gravity than the visible stuff can account for, which brings us squarely to dark matter.
The big elephant in the cosmic room, yes. Dark matter is this huge puzzle sitting right at the crossroads of particle physics, astrophysics, and cosmology.
And the evidence is strong.
Overwhelmingly strong, based on the sources. There's just far too much gravitational pull observed on all sorts of scales, from galaxy rotation curves to cluster dynamics to gravitational lensing, than can be explained by the stars, gas, and dust we can see. This points to a massive amount of non-baryonic dark matter.
Non-baryonic meaning not made of protons and neutrons like us.
Exactly. Not part of the standard model of particle physics. Its existence is one of the strongest pieces of evidence we have for needing new physics beyond that standard model.
So what could it be? What are the candidates discussed?
The sources mentioned several ideas, but they focused quite a bit on a class of candidates arising from a theoretical framework called supersymmetry, or SUPY.
SUPY, I've heard of that. Every particle gets a partner.
Sort of, yeah. In SUPY's way, every known fundamental particle has a heavier hypothetical superpartner. And many SUPY models predict that the lightest of these new neutral superpartners, often called the neutralino, would be stable.
Stable and dark.
Stable, electrically neutral, and interacting only weakly with normal matter, besides gravity. This makes it a prime candidate for what we call cold dark matter, or CDM.
Cold meaning slow-moving.
Right. It would have been moving slowly in the early universe, which helps it clump effectively to form the structures we see. And the sources point out that, quite remarkably, theoretical calculations suggest these neutralinos, if they exist with plausible masses and interaction strengths, could have been produced in the Big Bang in just the right abundance to make up the observed amount of dark matter. maybe even enough to make the universe flat, omega-1, which was a popular idea before dark energy was confirmed.
That sounds almost too good to be true. A particle predicted by theory just happens to have the right properties.
It's definitely a compelling convergence, which is why it's been a leading candidate for decades, but of course we need to find it.
How do you look for something that's invisible and barely interacts?
That's the challenge. This is where direct detection experiments come in. The basic idea is to build extremely sensitive detectors using very pure materials, place them deep underground to shield from cosmic rays and other background radiation, and then wait.
Wait for what?
Wait for one of these hypothetical dark matter particles, often generically called WIMPs, weakly interacting massive particles, which includes neutralinos, to occasionally bump into an atomic nucleus within the detector.
And that tiny bump leaves a signal.
A tiny, tiny signal, yes. Maybe a flash of light, or a tiny amount of heat, or some released electric charge. Detecting that incredibly rare, faint signal is the goal.
Is there any way to be sure it's a WIMP and not something else? A telltale sign?
One really sought-after signature is called seasonal modulation, or annual modulation.
Because of the season.
Because of the Earth's motion, our solar system is moving through the galaxy's dark matter halo, and the Earth orbits the sun. So throughout the year, the Earth's velocity relative to the incoming wind of dark matter particles changes slightly.
Okay, faster in summer, slower in winter, sort of.
Something like that, depending on the exact direction. This changing relative speed should cause the rate of WIMP interactions in a detector on Earth to modulate slightly over the course of a year. It should follow a specific cosine-like pattern, peak at a certain time of year, and crucially, only appear in the specific energy range expected for WIMP recoils, not across all energies like many backgrounds.
That sounds like a very specific fingerprint. Hard to fake.
Extremely hard to fake with known backgrounds, yes.
And the sources mention specific experiments looking for this.
They do. They highlight the DAMA experiment, located under the Gran Sasso Mountain in Italy. DAMA uses sodium iodide crystals and has famously reported observing exactly such a seasonal modulation signal for many years, consistent in phase and energy with what you'd expect from a WIMP.
So case closed. Found it.
Well, it's complicated. The sources also discuss other experiments, particularly the CDMS experiment, cryogenic dark matter search, which uses a different technology.
What do they use?
CDMS uses detectors made of germanium and silicon, cooled to extremely low temperatures. And they employ a technique called double readout.
Double readout.
Yes, they can measure two signals from each interaction. The tiny amount of heat deposited, phonons, and the amount of electric charge released, ionization. The key thing is that a WIMP, or a neutron hitting a nucleus, a nuclear recoil, produces a different ratio of heat to charge compared to, say, an electron or gamma ray hitting an electron recoil.
Ah, so they can tell different types of particles apart, discriminate backgrounds.
That's the huge advantage. It allows them to reject most background events very effectively.
And what did CDMS find? Did they see the DAMA signal?
This is where the tension arises, as described in the sources. CDMS did observe some events that looked like nuclear recoils, the type WIMPs should produce. However, after very careful analysis, looking at how many events hit silicon versus germanium, looking for events hitting multiple detectors, which WIMPs shouldn't do, and comparing with simulations of known backgrounds like neutrons scattered by cosmic rays, CDMS concluded that their observed nuclear recoil events were consistent with being caused by background neutrons, not by WIMPs.
So they didn't confirm DAMA.
More than that, based on their non-detection of a WIMP signal, CDMS produced exclusion plots. These plots show the region of possible WIMP mass and interaction strength that their experiment rules out. And according to the sources, the CDMS exclusion limits, assuming standard WIMP models and halo properties, strongly conflict with the region needed to explain the DAMA signal. They basically say, if DAMA is seeing standard WIMPs, we should have seen many more events than we did.
That sounds like a major disagreement.
It is. It's been a long-standing puzzle in the field.
Do the sources offer any way to reconcile this, or caveats?
They absolutely emphasize the uncertainties involved when comparing different experiments. You're using different target materials, sodium iodine versus germanium silicon, different techniques, and comparing them requires making assumptions.
Assumptions about what?
Assumptions about exactly how WIMPs interact with different nuclei, which involves nuclear physics. Assumptions about the WIMP's mass and other particle physics properties. And critically, assumptions about astrophysics, like the exact density and velocity distribution of WIMPs in our local part of the galaxy's halo. If any of those assumptions are wrong, the comparison breaks down.
So it's not necessarily that one experiment is wrong, but maybe our assumptions used to compare them are incomplete.
That's certainly a possibility the sources acknowledge. It highlights just how difficult these experiments are, searching for such incredibly rare events and the challenges in interpreting the results definitively.
Okay, so dark matter is still very much a mystery, but it seems essential for building the universe's structure. How does that structure formation actually happen with dark matter involved? How do we get galaxies and clusters?
Right, so the modern picture, laid out in these sources, involves dark matter providing the gravitational scaffolding. The idea is that dark matter, being collisionless and interacting mainly through gravity, clumps together first. It forms these invisible, roughly spherical structures called dark matter halos.
Halos, like invisible cocoons.
Exactly. Then, the ordinary baryonic matter, the gas, feels the gravity of these dark matter halos and falls into them. Inside the halo, the gas can cool down, lose energy, and collapse further towards the center, eventually forming stars in the visible galaxies we see.
So galaxies live inside much larger dark matter halos.
That's the paradigm. And clusters of galaxies are simply the largest, most massive dark matter halos, which have captured hundreds or thousands of individual galaxies within their immense gravitational pull. They form from the rarest, highest peaks in the initial density field.
How do we actually measure and describe the distribution of all this structure? Galaxies, clusters, dark matter across the cosmos.
We use statistical tools. Two really fundamental ones discussed are the correlation function, usually written as a calar, and the power spectrum, pK.
Okay, what do they tell us?
The correlation function, XIR, basically measures the excess probability of finding another galaxy, or halo, at a certain distance away from a given galaxy, compared to if galaxies were just scattered randomly. A positive XIR means galaxies tend to cluster together.
And the power spectrum.
The power spectrum, pK, is related through a mathematical operation called a Fourier transform. It describes the lumpiness or the amplitude of density fluctuations as a function of spatial scale, where k is related to Forn's scale. Big structures correspond to small k, small structures to large k. It tells you how much structure exists at different sizes.
And do galaxies perfectly map out the dark matter distribution?
No, and this is a crucial point the sources make. Biased clustering.
Biased, meaning unfair.
Not exactly unfair, but not a perfect representation. Galaxies and dark matter halos don't just passively trace the underlying dark matter density. They tend to form preferentially in the densest regions of the dark matter distribution. So galaxies end up being more clustered together than the dark matter itself, especially on certain scales. That's spatial bias. Okay. There can also be velocity bias, where the average motion of galaxies might differ slightly from the average motion of the underlying dark matter. Understanding and modeling this bias is really important when we use galaxy surveys to infer properties of the dark matter or cosmology.
And how do we study this bias?
Numerical simulations are absolutely key here. Running large computer models of dark matter evolution and galaxy formation helps us understand how bias arises and how strong it is under different assumptions.
What kinds of observations do we actually use to map out this large-scale structure across cosmic time?
There are several major observational probes. Galaxy surveys are a huge one. We map the positions and properties, like brightness, color, redshift, of millions of galaxies. From this, we can measure things like the correlation function, the power spectrum, and how the number density of galaxies, the luminosity function, changes with cosmic time.
What are the challenges with galaxy surveys?
Well, disentangling the effects of galaxy evolution, how galaxies themselves change over time, from the effects of the expansion geometry is tricky. There are also selection effects we tend to see only the brightest galaxies at large distances and things like dust obscuring our view. But measuring things like the overall star formation rate density as a function of redshift gives us a handle on the history of star birth in the universe. Cluster surveys are another powerful tool. As we said, clusters are the biggest collapsed things, forming from the highest density peaks. Their sheer number and how they are distributed are extremely sensitive to cosmological parameters, like the total amount of matter, omega, and dark energy, omega lambda.
How do you find and study clusters?
Often by looking for the hot gas trapped in their deep gravitational wells, which shines brightly in X-rays. Measuring the X-ray luminosity function, how many clusters exist at different X-ray brightnesses, or trying to estimate their total mass, gives us independent ways to constrain cosmology.
Are there surveys looking at even bigger scales? The really vast structures?
Yes, the sources mention surveys like Reflex, which was specifically designed to measure clustering on scales of hundreds of millions of light years. Interestingly, Reflex found potentially a bit more clustering power on these very large scales than some earlier estimates based on galaxy surveys might have suggested. It hints that maybe the universe is slightly lumpier on the biggest scales than the simplest models predict, though measuring things accurately on those scales is tough.
And these huge computer simulations we mentioned, how do they fit into understanding all this structure formation?
They're indispensable. N-body simulations, using codes like PM, P3M, RRT that the sources mention, follow the gravitational interactions of millions or billions of dark matter particles from the early universe conditions, like those seen in the CMB, right up to the present day.
So you can watch halos form.
Exactly. You can see how dark matter halos form, merge, and build up the cosmic web. These simulations are crucial for testing theoretical predictions against observations, for understanding things like halo mass functions, clustering bias, and even the internal structure of dark matter halos. The sources mention common models for halo density profiles, like the NFW profile or the Moore profile, which come largely from simulation results.
Do simulations have limitations?
Oh, absolutely. Computing power is always a limit.
Hmm.
There's a constant trade-off between the size of the cosmic volume you simulate and the resolution you can achieve accurately modeling. Both the formation of tiny dwarf galaxies and the largest clusters in the same simulation is incredibly challenging due to limitations in force calculation, time stepping, and particle mass.
Okay, so we have the CMB, expansion models, dark matter driving structure. The sources also talk about another powerful tool for probing mass, including dark matter, gravitational lensing.
Yes, gravitational lensing, one of the most striking predictions of Einstein's general relativity. The core idea is that mass curves spacetime, and light follows those curves.
So mass bends light.
Exactly. Any massive object, a star, a galaxy, a cluster of galaxies, even large filaments of dark matter acts like a lens, bending the path of light rays that pass nearby from more distant sources.
And this lets us weigh the lens, including the dark matter.
Precisely. Lensing is sensitive to all the mass along the line of sight, whether it's visible matter or dark matter. It doesn't care if the mass shines or not, only about its gravitational pull. The basic physics is described by the lens equation, which relates the true position of the background source to the observed position of its lensed image.
And lensing comes in different flavors, right? Depending on the alignment and the mass.
Yes, we usually talk about three regimes. Strong lensing is the most dramatic. This happens when the alignment between the source, the lens, and us is very close, and the lensing mass is concentrated enough, like a galaxy or cluster. This can produce multiple distorted images of the background source, long stretched-out arcs, or even complete circles called Einstein rings.
What can we learn from strong lensing?
It's fantastic for mapping the detailed mass distribution within the lensing galaxy or cluster, often revealing the distribution of dark matter. And in special cases where the background source is variable, like a quasar flickering, the light from the different multiple images takes slightly different paths and arrives at different times. Measuring these time delays can, in principle, allow you to measure the Hubble constant, though it's complex and depends on accurately modeling the lens mass distribution and knowing the overall cosmology.
Okay, what about microlensing? That sounds smaller.
Much smaller deflections, yeah. On the order of milliarcseconds, far too small to resolve separate images. Microlensing happens when a compact object like a star, planet, or maybe a primordial black hole passes almost directly in front of a background star.
You don't see multiple images, so what happens?
The gravity of the foreground lens focuses the light from the background star, temporarily magnifying its brightness. As the lens moves across our line of sight, the background star appears to brighten smoothly and then fade back down in a very characteristic, predictable way over days, weeks, or months.
And this has been used to look for dark matter.
Yes, collaborations like EROS and MACHO mentioned in the sources use microlensing surveys. They monitored millions of stars in nearby galaxies like the Magellanic Clouds, looking for these temporary brightening events. The goal was to see if a significant population of massive compact halo objects, MACHOs, things like brown dwarfs, isolated black holes, or faint stars in our own galaxy's halo could account for the Milky Way's dark matter.
What did they find?
They found some microlensing events consistent with known populations of low-mass stars, but generally not enough to account for the vast majority of the galaxy's dark matter halo, ruling out MACHOs in a certain mass range as the dominant component.
All right, so strong lensing, microlensing. What's weak lensing?
Weak lensing is about the very subtle distortions caused by the gravitational pull of large-scale structures, clusters, filaments of dark matter spread out across the sky. It's not strong enough to create multiple images or obvious arcs.
So what does it do?
It slightly stretches or shears the observed shapes of distant background galaxies. Imagine looking at distant circular galaxies through a slightly uneven piece of glass. They might appear slightly elliptical. The effect on any single galaxy is tiny, maybe a 1% change in shape, totally lost in the galaxy's natural variation.
How can you measure something so small?
Statistically, by measuring the shapes of thousands or millions of distant galaxies in a patch of sky and averaging them, you can pick out the coherent, tiny alignment pattern, the gravitational shear induced by the foreground mass distribution.
And that tells you.
It allows you to create maps of the projected mass density, including dark matter, over large areas of the sky. You can map out clusters and filaments, even where there's little visible light. It's become a major tool for cosmology. The sources do note a complication called the mass sheet degeneracy, which basically means weak lensing shear alone measures the mass distribution up to an overall scaling factor, making it tricky to get the absolute mass calibration without other information.
It's genuinely incredible the range of tools we have now. From the CMB's baby picture to supernovae, underground detectors, mapping galaxies, watching light bend.
The progress described in these sources, especially over the last few decades of the 20th century, really was transformative. Cosmology became a data-driven precision science.
But the sources also make it very clear that despite all this progress, there are still some really profound theoretical challenges and, well, unanswered questions still lurking out there.
Oh, absolutely. They don't shy away from the deep issues. For instance, they really emphasize how difficult it is to prove, purely from observation, that the universe is truly homogeneous on the largest scales.
Even with the CMB looking so uniform.
The CMB tells us the universe looks highly isotropic around us, the same in all directions. But proving it's truly homogeneous the same everywhere is much harder. The sources point out that current observations, like using supernovae as standard candles, aren't quite precise enough yet to definitively rule out certain inhomogeneous models where we might, just by chance, be living near the center of a large, spherically symmetric structure that only looks isotropic from our special vantage point.
So we can't be 100% sure it's not just an illusion of uniformity.
Observationally, there's still some wiggle room for inhomogeneity, though the standard homogeneous FRW model remains by far the simplest and best fit to most data.
What about theoretical arguments for homogeneity, like it's simpler or more probable?
The sources are quite critical of relying too heavily on those arguments. Appealing to probability, saying it's unlikely we'd be in a special place, therefore the universe must be homogeneous, is philosophically tricky. Mathematically, perfectly homogeneous models are actually less general, have fewer degrees of freedom, than inhomogeneous ones.
So they're maybe less probable, mathematically speaking.
You could argue that. And applying probability to the unique universe we inhabit is fraught with difficulty. The sources also touch on the anthropic principle of the idea that we see the universe this way, because only such a universe could allow observers like us to exist.
What do they think of that?
They pretty much dismiss it as being untestable, metaphysical, and not really a physical explanation in the scientific sense.
So if observational proof is hard and philosophical arguments are shaky, what's the status of ideas like chaotic cosmology or inflation in explaining homogeneity?
They're seen as attempts to provide a physical mechanism for why the universe looks so smooth and flat today, even if it didn't start that way. Inflation, as we discussed, dynamically smooths out initial wrinkles and flattens geometry through its rapid expansion. Chaotic cosmology scenarios explore the idea that even if the universe started in a very messy, arbitrary state, regions where inflation did occur would expand enormously, creating vast, smooth domains like the one we presumably inhabit, separated by complex boundaries from other regions that might have inflated differently or not at all.
So we just happen to live in a big inflated bubble.
That's the rough idea in those scenarios. It makes homogeneity a likely outcome within our observable patch, even if the multiverse beyond is chaotic.
And then, the sources get into perhaps the deepest question of all, trying to explain the origin of the universe itself, from nothing.
Yes, and here they express profound difficulty, maybe even hinting at the limits of our current understanding. The challenge is trying to formulate the question, let alone answer it, using physics. Most attempts to describe an origin from nothing still implicitly assume the pre-existence and validity of fundamental physical laws, like quantum field theory, operating perhaps on some pre-geometric state. But the sources question how physics and the associated concept of causality can even exist or operate before space-time and the universe itself, which are supposedly emerging from those laws.
Our language breaks down.
Exactly. Our concepts of before-cause effect are all rooted in spacetime. Trying to apply them to a state where spacetime itself doesn't exist, well, the sources put it bluntly.
What do they say?
They state, our language can hardly deal with this. And they go on, there cannot be a prior physical explanation precisely because physics and the causality associated with physics does not exist therein. It's a stark reminder of the potential boundaries of scientific explanation when confronting the ultimate origin question.
Wow. Okay. Well, we have definitely covered a huge amount of cosmic territory in this deep dive.
We really have. We've gone from the CMB, that relic light carrying the imprint of the early universe's sound waves,
Through the models of expansion, the discovery of acceleration driven by dark energy.
explored how structure grows via gravity, acting on seeds within a scaffolding of dark matter.
And looked at how we probe all this with everything from supernovae and galaxy surveys to underground detectors and the bending of light via gravitational lensing.
It's clear from these sources just how much cosmology transformed into a real, data-rich science, making incredible strides.
The convergence of evidence from so many different angles is truly remarkable.
It's a triumph of the scientific method applied to the grandest scales.
But, as the sources also powerfully remind us, there are still these massive, fascinating questions out there. Maybe we feel even further from a complete understanding than we might have thought before uncovering things like dark matter and dark energy.
That frontier of the unknown is precisely what makes cosmology so exciting, though. Always new puzzles emerging.
So let's leave you with a final thought to ponder, drawn straight from these expert insights. Despite this incredible journey, turning ancient wonderings into testable physics, the most fundamental mysteries persist. What is the ultimate origin? What is the true nature of the dark, 95% of the universe? Can we ever truly know the universe's ultimate geometry with absolute certainty? These questions remain profoundly challenging.
They push right up against the limits of what physics, as we currently understand it, might be able to explain.
They definitely invite us to keep looking up, keep simulating, keep experimenting, and keep asking those deep questions. Thanks for diving into the cosmos with us today. We really hope exploring these sources and the insights from the experts tackling these problems has been valuable for you.